All right, today we're going to try to understand nuclear decay rates, and we want to use that in order to be able to calculate the age of something. Now, before we get into any kind of calculations, I want us to think about an important question. Why is it so hard to get rid of nuclear waste, right? Nuclear waste is a problem, but why? And in order to answer that question, let's first think about, well, what do we do with ordinary waste? Now, ordinary waste we can simply, let's say, throw in the ground, put in a landfill somewhere. But if it's toxic, we're going to do something with that. So typically, your non radioactive toxic waste can be burned or can be chemically reacted to turn it into something safer. All right. But you can't do that with radioactive waste. Radioactive waste cannot be made safer by reacting with something. Right? Your nuclear decay of any kind of radioactive substance cannot be sped up or slowed down, let's say by heating it up, cooling it down, or reacting with something. No, instead, the rate of decay is going to only depend on the amount and the type of radioactive material that you have. All right. And so you can't change it. It's going to always be radioactive until all of it has reacted and turned into some non radioactive element. So, the way that we can understand this fixed rate of decay of radioactive materials is something known as the half life. Okay, so a half life is a constant for a particular radioactive isotope. So if we look at, let's say, uranium 238, which is the most common form of uranium on Earth, it has a half-life of 4.5 times 10 to the ninth. That's 4.5 billion years. So it takes 4.5 billion years for half of the amount of uranium 238 in a substance to turn into something else. Okay. Now, these half-lives, we have tables of these. These half-lives are constants. That means they don't change. So uranium-238, it always has a half-life of 4.5 billion years. We can't change that. You can't, let's say, react uranium with some other element. You can't make, let's say, uranium oxide and think that that half-life is going to change. No, it's always going to be this, no matter what uranium is bonded to or not bonded to. Okay? Now, these half-lives do differ from isotope to isotope, and they differ quite a lot. So if we look, let's say, down here for carbon-14, carbon-14 has a half-life of 5,715 years. I've seen it sometimes as 5,730 years, but it's a lot less than this 4.5 billion years of uranium-238. And then if we look at, let's say, some synthetic isotopes or human-made isotopes, one of them like iodine-131, it has a half-life of significantly less than a year, 0.022 years, and so it's going to decay a lot faster. Now, what is this half-life? How can we understand what half-life really is? And I think this graph kind of explains it all, right? So let's check this out. This is strontium 90, and we're starting with 10 grams of strontium 90. And let's see what happens. So if we're starting with 10 grams, this right here, the shaded represents 10 grams of strontium 90. After one half-life, you have only half of the amount of strontium 90 that you started with. Well, what is that? That's going to be 5 grams. So we started with 10 grams, and we're going to end up with 5 grams of strontium 90 after one half-life. And we can follow this down to the x-axis and see where that shows up here. And that looks like, so if we have 30 here, that looks like 27 or 28 years here as the half-life of strontium 90. So this is one half-life. This is going to be 2 half-lives. This is going to be 3 half-lives. And after one half-life, half of the amount of strontium 90 that you started with turns into something else. After 2 half-lives, half of this material is now going to decay and turn into something else. And so you're left with now 1/4 the amount that you originally started with. Okay. And that's going to be what? So it's going to be half of 5 or 2.5 grams. After 3 half-lives, half of this is now going to decay, and you're going to be left with 1/8 of the original amount you started with. And that's going to be about 1.25 grams, which you're going to see right over here. Okay. And so every half life, you progressively react or remove half of the amount of material that remains. And you're going to progressively get less and less of the material. So we can use this concept and these numbers of half-lives to actually figure out how old something is. Let's say we're trying to figure out how old a particular rock is. And we can use what's typically done is, well, there's a lot of different methods, but one of the most common ones is using potassium 40. Potassium 40 is a naturally occurring radioactive isotope, and when it decays, it turns into argon 40. And we can look at this diagram and see kind of how that happens. The half-life of potassium 40 is 1.25 billion years. So after one half-life is 1.25 billion years, you're going to get half of this potassium 40 turning into argon 40. And you can see that represented by the green ones represent potassium 40, the yellow ones represent argon 40, and we now have about 50-50 potassium 40 and argon 40. And that those relative ratios are going to let you know how much of that potassium 40 has decayed into your argon 40. So you don't need to know necessarily the original amount of potassium 40 because now you have it turning into argon 40, and you can look at the relative amounts of potassium 40 and argon 40 to figure out how old the rock is. Okay, so after one half-life, you have this 50-50 amount, and you can tell, okay, that rock is about 1.25 billion years old. Okay, after two half-lives, you now have more argon 40 than potassium 40, and that ratio is going to tell you, okay, now you have two half-lives, and that's going to be 2.5 billion years old, et cetera, et cetera. Okay, now we have an equation that we can use to deal with any kind of ratio that you have of those two different materials. Now, carbon-14 is also another common way to date something that's fairly old, but carbon-14 is used for organic substances, things that were once living, and it's going to be used for things that are not too terribly old, and things that are, let's say, in the thousands of years old rather than millions or billions of years old. Carbon-14 dating is occurs because you get carbon-14 at a fairly constant amount due to cosmic radiation. Okay, and so you might think, well, carbon-14 with a half-life of only, let's say, 5,700 years or so should be all gone by now. But it's not, because we have a certain amount of carbon-14 that's always being produced in the atmosphere. So cosmic radiation, which either comes from the sun or comes from various different things in outer space, is composed of a bunch of different things. Primarily, it's going to be, let's say, protons and neutrons that are going very, very fast. When they come into our atmosphere, most of them are going to be deflected by Earth's magnetic field, but some of them are going to come into our atmosphere. They're going to interact with the gases in our atmosphere. And the most important gas, or the most prevalent gas in our atmosphere, is nitrogen, N2. Nitrogen is typically going to be nitrogen 14. However, when it's bombarded by this cosmic radiation through a number of different steps, that nitrogen 14 can actually turn into carbon-14. Okay. And the carbon-14 is then going to go on to, let's say, react with oxygen in the air to turn into carbon dioxide. And that carbon dioxide now is going to be carbon dioxide that has carbon-14, and carbon-14 is radioactive. So, how does that get in our bodies? Well, carbon-14 is going to be part of carbon dioxide, and plants in all over the world are going to absorb that carbon-14. How? Through photosynthesis. So, trees and various different other kinds of grasses and plants are all going to do photosynthesis, and they're going to incorporate some of that carbon dioxide in all of the entire plant. And what about animals? Well, animals, they eat fruit, they eat grass, they eat plants. And because they're eating these organic materials, these plants, then now they're going to also incorporate this carbon-14 in their bodies. And even if you're not a plant eater, if you're a meat eater, you're going to eat something that at some point has eaten plants. And so carbon-14 is going to be present in all life. Everything that's living is going to have a certain amount of carbon-14 in it, based on the amount of carbon-14 in the atmosphere, because of photosynthesis and because we eat things that are living. Okay, so once something dies, and this is the key here, once something dies, no more carbon-14 is added, right? And so therefore, once something dies, well, while something's alive, the amount of carbon-14 in it is going to remain constant. It's going to remain more or less the same as it is in the atmosphere. But once something dies, no more carbon-14 is added. And so now the clock starts, and carbon-14 is going to decay at its typical half-life decay. And so you can tell how old something is, and basically how old something is or when something died based on how much carbon-14 there is in it. The less carbon-14 is in something, the older it is. The more carbon-14 is in something, the closer it is to having just recently died. Okay, so as something gets older and older and older, it's going to have less and less carbon-14 in it. Now, carbon-14 dating can only be used for organic substances, and it can really only be used for things that are no more than 50,000 years old. Why? Well, first of all, because something needs to have been alive in order to take in carbon-14. Rocks don't have carbon-14. They can't have carbon-14. The rocks are not incorporating carbon-14 from the atmosphere in them. And the half-life of carbon-14 is about 5,730 or so years. So after 10 half-lives, after, let's say, 57,000 years, there's really not going to be enough left for an accurate measurement. Each of those half-lives is progressively going to take half of the remaining material and turn it into something else. So there's not going to be much left after 10 half-lives. All right. One other thing to note about carbon-14 dating is it assumes the constant amount of cosmic rays, right? Because cosmic rays create that carbon-14 in the atmosphere. Now, the cosmic rays, it would make sense that they're fairly constant. However, we also have to remember that that would mean we have a constant amount of or constant magnetic field from the Earth. And if that magnetic field changes, you could actually change the amount of cosmic rays entering the Earth, which could change the amount of carbon-14 in the atmosphere. That's typically a pretty good assumption, but the magnetic field has been known to change somewhat over time. And so that's something to consider when considering carbon-14 dating. All right. So these are the equations that we're going to be using to do any kind of carbon-14 dating or any kind of radioactive or radiometric dating of any kind of material. Okay. So this equation right down here is going to be used for the age of something. So if we want to figure out the age of something, we're going to use this equation right here. Okay. And the top equation, we're going to be using the top equation if you want to figure out how much of a substance remains after a given amount of time. And so we can look at, well, what are all these different things mean? T1 half, that's going to be the half-life of the material, and that's going to be a constant. T is going to be the amount of time that has gone by. And so T, we can find out in this equation, we want to figure out how much time has gone by or the age of something. That's going to be this T right here. N is the amount of radioisotope that you have when you measure it in a given sample. So N right here is the amount of radioisotope that you have. And 0 is the amount of radioisotope that you started with. Okay. And so typically you don't necessarily know exactly what that's going to be, but you can get this ratio, right, of the N over N0, the amount of radioisotope that you have over the amount of radioisotope you started with. And you can look at that ratio like we talked about for the potassium argon example. And so we can think about, well, for example, your N over N0 is what? It's going to be 1/2 after 1 half-life of time. And so the amount you have is going to be half of the amount that you started with. And so this N over N0 ratio is going to be 1/2 after 1 half-life of time. So let's go ahead and try to do a few of these sample calculations. All right, I want to try a couple sample problems to make sure that we understand how to use those equations that we've been given. And let's start off with this one. So the half-life of carbon-14 is about 5,730 years. If one sample originally contained 4 grams of carbon-14, how much carbon-14 would be left after 25,000 years? So anytime you're dealing with something that's calculating the amount of material, how much stuff that you're getting out at the end of the day, we're always going to be using the equation that you have first there. So that's going to be N over N0, so the amount of stuff that you have at the end of the day, divided by the original amount. And this is going to be equal to a half to the power of T divided by T1 half. So this part up here, this exponent, essentially is telling you how many half-lives have occurred. So for example, if you're talking about after 5,730 years, this T would be 5,730 years, and then T over T1 half would be 1. And so this would be 0.5 to the first power, which would then be just 0.5, or 1/2. So you have half the amount of material that you started with. Okay, but that's not what we have in this case, so let's go ahead and plug in some numbers for what we have in this case. Okay, so we have, so N, that's what we're starting with, right? So how much would be left? Okay, so we're starting with, that's the amount that we're calculating. So we don't know N, we want to figure out N. So N over N0. Now, sometimes you don't know N0, but in this case we do. So it says the sample originally contained 4 grams. So this is going to be 4 grams of that stuff, right? And it's going to be 0.5 to the power of T over T1 half. And this T is the amount of time that elapsed, which is 25,000. So this is 25,000 divided by the half-life, which is 5,730. Okay? And so you can do this calculation, and then N is simply going to be 4 times that. So we're just going to multiply both sides by 4 in order to get the final value of N. So let's go ahead and plug this in the calculator, and let me show you the process that I'm going to do that. Okay? So let's start off over here. I'm going to start off, and you could probably put this all into one line, but I think it's going to be easier if we just do our this fraction right here. So it's going to be 25,000 divided by the half-life of 5,730, right? 5,730, okay? And so that tells us that you have 4.36 half-lives have occurred. 4.36 half-lives. And so we're going to do 0.5 to the power of the number of half-lives you've had. We can just use the previous answer. We're going to get that. And so this is the value of N over N0. So it's the fraction of the original remaining. And so what we can do is we can just multiply both sides by 4 now in order to get that. So it's going to be, let's go ahead and do this. So N over 4 grams is equal to this 0.048, and they just round it up 6. All right, and so we're going to multiply that by 4, and that's going to give us our value of N, or the amount of stuff that is remaining, and that's going to be 0.194. And the units, of course, are going to be grams because we started off with grams. So we started off with 4 grams of carbon-14 in the material, and we ended up after 25,000 years with only 0.194 grams. So we have a whole lot less carbon-14 in this material. Okay, now if you want to figure out the age of something, which is what we're doing down this problem, so here we have an old cloth, and we are testing it, and we've got a certain amount of carbon-14 in it, and we want to know how old. Anytime you're doing an age question, we're going to be using the one that starts with T equals. Okay, so it's going to be the age is going to be the half-life times the natural log of this N over N0 over the natural log of 0.5. Okay, and this 0.5 is going to be standing for the the half-life here, or because we're dealing with half-lives and we have to use natural logs. Now you can use ordinary logs to do this. It'll work the same way with ordinary logs. But let's go ahead and plug in some numbers. And it might at first not be entirely obvious what all do we plug in here, but let's go ahead and do that. So this is the time, the age that we're calculating. The half-life here is still the same. It's going to be 5,730 years. And we're going to multiply this by the natural log of n over n0. What is that? What's this n over n0? Well, that's going to be your 75%, okay? You have 75% of the amount of carbon-14 it originally had, which means that if it started with, let's just give you an example. If it started with, let's say the original was 100 grams, then you would have 75 grams after that certain amount of time. Now, you probably don't have that large of amounts, okay? But that fraction is going to be the same either way. Okay, this is going to be the natural log of 0.75. So that percentage is going to go right in here. That percentage is, this is your n over n0 fraction. That's what that is in percent form. Okay, so we're going to take the natural log of that, divide by the natural log of 0.5, and we're going to get our final answer. So let's go ahead and plug in some numbers to get the age of this thing. Okay, so first up, let's do the natural log of 75 over 100. I'm going to divide that by the natural log of 0.5. And we get out 0.415, okay? And then that's essentially telling you how many half-lives have occurred. And so we have less than one half-life. Does that make sense? Well, yeah, we have 75%. So this is more than half of the amount of material. So we're expecting something that's less than one half-life. All right, and that's exactly what we have. We have 0.415 half-lives. And so you can go ahead and write down this number. So this is 5,730 years, right? And we had 0.415, and that's the number of half-lives that we had right there. And let's go ahead and do that multiplication. Times 5,730, and it gives us 2,378. 2,378. Now we probably really only have two significant figures here, so you can't say it to four significant figures. So really it's going to be 2,400 years old, you know, more or less, give or take. So this could be 100 years off, right? Because we only had two significant figures here, and even in our initial half-life here, we might only have three significant figures. So we have two significant figures here for our answer, and that is it. All right, so have a good one, everyone. See you guys.